We can display complex numbers in the complex plane shown here, or what's called the Argand diagram. And our complex number in this case is 4 plus 3i. The 4 represents the real part, and we can show that on a horizontal axis. And the 3 is the imaginary part, and that's represented on the vertical axis. And we can see here that we've got a point which represents the number 4 plus 3i. We've also drawn a vector from the origin to the coordinates of 4, 3, and that's another way to represent this complex number, which will be useful in future calculations. Let's have a look at some terminology involved with the complex number. The modulus is the length of that vector from the origin to the coordinates 4, 3, and we can work that out as we would do in any right-angled triangle. So we'll let the length be d, and we'll calculate the length d using Pythagoras. So d squared is equal to 3 squared plus 4 squared. And following through in that calculation, we can see that the value of d will be 5 units. And that's our modulus. Another term that we use here is the argument of a complex number. And that's the angle between the vector and the positive x-axis. Given that we have a right-angled triangle and we have the sides opposite and adjacent to the angle, we can use the trigonometric ratio tangent. So tan theta is equal to 3 over 4, or opposite over adjacent, and that gives us our angle, in this case 36.87 degrees. So that's the argument of this complex number. Now the way we've expressed the complex number here, 4 plus 3i, is regarded as being in Cartesian or rectangular form because it refers to the coordinates 4 and 3. There is another way though to express a complex number, and that's in polar form. Before we do that, let's have a look at how we might associate an angle and a hypotenuse, or actually a modulus and an argument, with the vertical and horizontal aspects of that complex number. So we can see here that if we've got a triangle with a 30-degree angle and a hypotenuse of 8, we can express the vertical side as 8 sine 30. And likewise, if we want to express the length of the horizontal side, we can use cosine. So the horizontal side is 8 multiplied by cosine 30. So now we've expressed our original complex number 4 plus 3i in polar form. Let's have a look at how it works. You can see at the beginning of our expression at the bottom of the screen that we've got the number 4 for the horizontal component, and that matches 5 multiplied by cosine 36.87 degrees. In other words, the modulus multiplied by the cosine of the argument. If we then look at the vertical part, which is the imaginary part of our number, which is 3, we can see that the 5, the modulus, because it's outside the bracket, that's also multiplied by sine of 36.87. So that gives us the vertical component of our complex number. So 4 plus 3i is what's called Cartesian or rectangular form, and the form on the right-hand side of our equation at the bottom of the screen is said to be in polar form, where we have the modulus and the argument within that expression. In our next example, we have the complex number expressed in Cartesian form, negative 2 root 3 plus 2i. So we've formed a triangle again using our vertical and horizontal components, and we can work out the modulus using Pythagoras. When we do that, we get a result of 4. Like before, we can use trigonometry to work out the argument for this complex number. But when we do this, we're working out the angle in the right-angled triangle shown on the screen. This is not actually the argument. The argument is the angle that's made with the positive x-axis. So when we get our result here of 30 degrees, the actual argument is 150 degrees. And we achieve that by going 180 degrees, which is the angle all the way through to the negative x-axis, and subtracting 30 degrees. And that gives us the angle that this vector makes with the positive x-axis. And that's our argument. And of course we can recall that the modulus is 4. In our next example, the complex number in Cartesian form is negative 4 minus 4i. Now to work out the modulus, we can use Pythagoras. Again, we'll represent the hypotenuse with d. And going through and using the Pythagorean formula, we can see that the distance is equal to the square root of 32, and that can be expressed as the square root of 2 multiplied by the square root of 16, or 4 root 2. Now, to determine the angle that will help us work out the argument of this complex number, we can again create a right-angled triangle and use trigonometry. and by using tangent we can get an angle of 45 degrees. Now, to work out the argument for the angle in this particular complex number, we need to take into account the following. The angle can be anything up to 180 degrees. That's from the positive x-axis to the negative x-axis, and that's shown here with the green arrow. But going in the negative direction, the angle can be down to negative 180 degrees. That's indicated there in orange. So in our example, we found that 45 degrees was the angle within our triangle, and we've shown that here in blue. So therefore the argument is negative 135 degrees. We've marked a 135 degree angle in our diagram, but of course that's going in the negative direction. So our complex number in polar form is 4 root 2, and in brackets cosine negative 135 degrees plus I sine negative 135 degrees. Now when we express a number in polar form, we can actually abbreviate that to what's called cis form. And the cis stands for the notation you can see in the bracket, which is the cosine and the imaginary value I and sine. So cis negative 135 degrees is the same as cosine negative 135 degrees plus I sine negative 135 degrees.